In this lesson, we're going to talk about pressure. Pressure is force divided by area. In physics, the standard unit of pressure is pascals. 1 pascal is 1 Newton per square meter. And 1 kilopascal is 1,000 pascals. And 1 atm, or atmospheric pressure, is 101.3 kilopascals. So those are some units that you want to keep in mind. So whenever you exert a force over a given area, that force exerts a pressure throughout that area. So pressure is simply force over area. Now what happens if you increase the area but use the same force? Let's say if we doubled the dimensions. Now if you apply the same force over, let's say, a larger area, the pressure is going to be a lot less. Let's say if we apply a force of 100 newtons. The pressure in this example is 100 divided by 1 square meter, so it's 100 pascals. In the second example, the area is 2 times 2, which is 4. So the pressure is now a force of 100 newtons divided by an area of 4 square meters, so it's 25 pascals. So what you need to understand is that if you increase the force applied, the pressure increases. If you increase the area in which that force is applied, the pressure decreases. The pressure is directly related to the force, but inversely related to the area upon which that force is applied. Let's try this problem. A 15 kilogram rectangular block with a length of 70 centimeters and a width of 40 centimeters rests on the table. What pressure does the book exert on the table? So let's say this is the book. And it's on a table. Now that book is going to exert a weight force on the table. And that force is applied over the area of the book, the bottom area. Now we have a length that's 70 centimeters and a width of 40 centimeters. And we know that pressure is force divided by area. And the force that the book exerts is basically the weight force of the book, which is mg. So the pressure exerted by the book is just mg divided by the area of the book. So the mass of the book is 15 kilograms. The gravitational acceleration is 9.8. And the area, let's get it in square meters. So to convert centimeters to meters, divide by 100. 70 centimeters is 0.7 meters and 40 centimeters is 0.4 meters. So 15 times 9.8. So that's going to give us a force of 147 newtons. And 0.7 times 0.4, that's going to give us an area of 0.28 square meters. So if we divide these two numbers, the pressure exerted by this book alone is 525 pascals. So this is the answer. Number 2. A closed rectangular container with dimensions 4 meters by 5 meters by 6 meters is filled with water. What is the pressure exerted by the water on the bottom face of the container? So let's draw a rectangular container. and it's filled with water. Now our goal is to find the pressure that's exerted by the weight of the water on the bottom surface of the cube. So how can we do that? Well, we know pressure is force over area. And keep in mind the density of water, if you're wondering, is 1,000 kilograms per cubic meter. Now, the force is the weight of the water, which is mg. And we don't have the mass of the water. However, we know that density, which is rho, is mass over volume. Don't confuse this with pressure. So the mass of the fluid, if we multiply both sides by V, is density times volume. So the pressure of the fluid is going to be the mass, which is density times volume, and then times gravitational acceleration, divided by the area. Now, the volume of, let's say, this rectangular prism is the length times the width times the height. So let me write that somewhere. Now, the length times the width will give us the area of the bottom surface. Or rather, I'm just going to replace volume with length times width times height. And the area of the bottom surface is just the length times the width. So we could cancel L and W. So the pressure that's due to the weight of the water alone is going to be the density of the fluid times the gravitational acceleration times the height of the fluid. So here it is. This is the equation that you want to keep in mind when dealing with the pressure due to a fluid. So we know the density of water is 1,000 kilograms per cubic meter. We have the gravitational acceleration, it's 9.8, and the height of the fluid. Now let's say the first one is the length, the second is the width. So the height, we're going to say it's 6 meters in this example. So it's going to be 1,000 times 9.8 times 6. So the pressure is 58,800 pascals. So that's the pressure due to the weight of the water alone. Number 3. A closed cylindrical container is filled with a fluid that has a specific gravity of 1.7. What is the pressure exerted by this fluid at a depth of 15 meters? So let's say this is the cylindrical container, and it's closed, and it's filled with some fluid. So at a depth of 15 feet, not feet, but 15 meters, let's say at this point, we want to know what's the pressure exerted at that depth. So we can use this equation. The pressure is equal to the density times gravity times the height. So if you have a fluid and you want to find the pressure exerted by the fluid alone at a certain depth, this is the equation that you can use. Now we need to know what the density of this fluid is, and we're given that specific gravity. The specific gravity is the density of the substance, in this case the density of the fluid, relative to the density of water. So the density of the fluid is going to be the specific gravity times the density of water. So we have a specific gravity of 1.7, and the density of water is 1,000 kilograms per cubic meter. So the density of the fluid is 1,700 kilograms per cubic meter. Now we have the gravitational acceleration, and the depth is 15 meters. So it's 1700 times 9.8 times 15. So the pressure exerted by this fluid at a point where it's 15 meters deep is 249,900 pascals. And if you divide that by 1,000, you could say it's about 249.9 kilopascals.